So we were talking about dynamic optimization methods. So here is the setting. Xt plus 1 equals to ft of xt ut. And I have a cost function j of u to be ct plus 1 xt plus 1 plus summation t equals 0 to capital T ct xt ut. I want to minimize this particular cost function. And the challenges that we were talking about in the previous class, T is large, FT, CT are complicated, and the third one was storing, how to store. VT and CT, VT and MUT. How to store the value function and the policy that we had computed using dynamic programming. So in the context of maximum principle or PMP, Pontryagin minimum principle, we didn't have to worry about storing VT and mu star T. We don't have to store any function there, primarily because you get an open loop solution. So you get U1 star, U2 star all the way up to UT star. So I don't have to store anything. I just have to store a bunch of vectors. Is storing a bunch of vectors a difficult problem in computers? What do you think is the dimensionality of the vector that you can store on a regular RAM? What dimensional object can you store on a usual, let's say 8 gigabytes RAM? So roughly, if you think about it, you have, to give you an idea, you have 8 gigabits. Let's say 8 bits is used to represent one number. Of course, you can use float 64, but if you're using 8 bits to represent one number, then you can have 10 raised to 9 numbers stored in a RAM. That's a fairly big vector, right? So you can store a pretty large vector. So that's why in PMP, when we were talking about Pontryagin minimum principle, I don't have this third problem. I might have the second problem, I might have the first problem, but I don't quite have the third problem. But I have the third problem now in dynamic programming. Remember I had said when we were talking about dynamic programming, we had said that we can have an infinitely long lookup table for mu star and VT, and that would help us run the dynamic programming algorithm. But now I don't have, I have finite memory. I have 8 gigabits of RAM on the rocket that I'm sending to space, and it has to come back. So how am I going to store all this value function and the policy that I'm computing using dynamic programming? What do you think? What would you do? So you put yourself in the shoes of, so there were people in Hidden Figures movie who were figuring out what the trajectory is. That was the movie. The movie was about those principal characters, but there were other people working in the background who were actually figuring out how to put all of this stuff in the computer, right? So imagine, put yourself into the shoes of that particular person, and it's your responsibility. Somebody else came up with the reference trajectory and all that stuff, who basically solved this first two problem. Now your problem is to solve this VT and MUT star storage. What would you do? Okay, so this is where any thoughts? Anybody wants to chime in? Yeah.
If you don't need the vector at like a given time, like maybe you could try some compression, so like store.
Wonderful, yeah. So wonderful. So you have this huge lookup table. You want to probably use some sort of compression to compress the lookup table. So what's a good way to compress a lookup table? What are people using nowadays to compress large amounts of data?
If it's an image, I mean, discrete cosine transform or whatever JPEG uses.
Right. Okay. So discrete cosine transform, yeah. So certainly JPEG uses some of those techniques. Those are signal processing techniques or wavelet techniques. But actually, I mean, technically speaking, you can do something like that. But the one that people are using nowadays is neural networks. And you can use neural networks, transformers, kernel methods, and so on. A lot of stuff in the machine learning area is about storing functions and storing lookup tables and compressing lookup tables. So if you think about statistical machine learning or machine learning as a field, it's all about compressing huge amounts of information into a single model, and that model essentially ends up doing everything. So essentially, you can store the value functions and the policy in the form. So instead of having it as a lookup table, you can train a neural network, and then you can store the policy or the value function in the lookup in a neural network or some sort of function approximator. So over the next few days, at least until the end of the semester, I'm going to talk about look ahead approximation, LQR problem and singular perturbation problem, which is the number two, solving number two. And the third one is universal function approximation theorems, which essentially solves number three. And that will complete our discussions on approximate dynamic programming, which is what we are going to talk about until the end of the semester. A good book on approximate dynamic programming, not a book, but like if you want to understand this whole subject much better, a good book is Dynamic Programming and Optimal Control. So, chapter 6 of this particular book deals with approximate dynamic programming, and much of the stuff that I'm going to talk about is actually from that chapter. So, I'm now collating information from a large number of sources in order to present in the class, primarily because I've seen that these topics are recurring topics in many students' research. So, I want to present that so that you're prepared for whatever research track you want to work in the future. So for T is large, I'm going to talk about rollout, algorithm, and I'm going to talk about model predictive control, MPC. Let me write the full form. Model predictive control. For FT and CT is complicated. I'm going to talk about singular perturbation. And I'm going to talk about LQR. We have quite a few work. I mean, not quite a few, but we have some work on the previous students who have been in this class, and some of them have been my PhD students. So they have worked on rollout algorithm, and they have worked on singular perturbation results. And then VT and MUT star, I'm going to talk about universal function approximators. And within this, I'll talk about neural networks. I'll talk about decision trees and many more topics. There are lots of different ways to compress a lookup table, and transformers is just one of the ways, by the way. It just falls under the umbrella of neural networks. So we'll talk about some of those universal function approximators in the class. So that will give you a bird's eye view of how to solve complicated dynamic optimization problems, especially if you're solving a real world problem. I think the approximate dynamic program theory that we will be talking about in the class, there are a few, say, theory papers or theory activities that people tend to do. We've done something in singular perturbation, but largely most of the tools and techniques are used in practical settings without necessarily appealing to theory, because theoretically it's very difficult to prove that these methods will work for the specific problem that you might be dealing with. But in practice, it's going to give you very good results. So that's why we end up using these class of algorithms. So any questions so far on this stuff? Is the roadmap clear for the next 5 or 6 lectures? Okay, so on Wednesday, of course, we don't have a lecture because it's a midterm too. But Friday onwards, we'll talk about some of these stuff. Before I proceed, I want to take a detour, and I want to talk about constraint dynamic program. So just trying to extend the dynamic programming algorithm here to the constraint version of dynamic program, uh, because it will be used for many of the stuff that we'll be talking about in the future. Okay. So what's the setting? The setting is exactly the same. I have the state transition. I have the cost function I want to minimize. Let me use, instead of u, I'm going to use pi, because were we using mu or pi for policy? Can someone check? Sorry? For policy, what were we using? Mu? Pi? Okay. Okay, so we are using pi. So I'm going to use pi here. Minimize overall policies pi. Ct plus 1 xt plus 1 plus summation t equals 0 to t. Now we have some constraints. Gt of xt ut less than equal to 0. Ht of xt ut equals to 0. This is known as state action constraints. And there are constraints like this at every point of time. What kind of constraints would inequality constraints have? So I'm driving a vehicle on the road. There is a vehicle in front of me, and I have to maintain at least 5 meters, 10 meters, 20 meters from the vehicle in front. So whenever you have like at least, so I can be 50 meters behind the other vehicle, that's fine, but at least 15 meters distance has to be maintained. So that would be a form of an inequality constraint. What about equality constraints? Where do equality constraints appear? Typically when some physical quantity is getting conserved, like energy, right? So I have some battery pack in the vehicle, and the battery pack is supposed to control the motor which is driving the vehicle, and it's also supposed to control the air conditioning system, and so the energy needs to be split between the two, and that's the so some conservation law needs to be maintained. Then you will have equality constraints in the system. Generally speaking, most problems that you would encounter will have a large number of inequality constraints. You could have upwards of 15, 20, 30 inequality constraints, and you might have just 2 or 3 equality constraints in your problem statement. So you have a lot more inequality constraints than equality constraints. Sometimes you would also encounter a problem where you will have xt plus 1 should be less than equal to 5 or whatever, some lower bound and upper bound. Let's say a less than equal to xt plus 1 less than equal to b. And remember that xt plus 1 is purely a function of xt and ut. So you just replace it, sorry, a xt plus 1 less than equal to b. You just replace it with a less than equal to ft xt ut less than equal to b. So then again it becomes inequality constraints of this type. Okay. Any questions so far? So whenever you have absolute state constraint that the velocity cannot be above, so velocity is a state of a vehicle, velocity cannot be above 70 miles an hour because that's the upper limit on the velocity. So that's xt plus 1 less than equal to b constraint. But remember, you're not really solving for xt plus 1 anywhere, but xt plus 1 is actually a function of the current state and the action. So this is what the constraint you should impose. Now, when you are solving a problem, one problem that you always, when you are solving a problem of this type, one problem that you always have to face and you have to somehow convince yourself is that there is always a policy pi that's going to meet all of these requirements. You can put a lot of requirements on the system, but the fact of the matter is that the policy may be infeasible. Like there's no policy that satisfies all the constraints. So that's something that you will have to somehow convince yourself that you're not putting constraints on the system in a way that things become infeasible. Okay. What are the situations where what happens in real world when there are things that are infeasible? What do you think happens?
Like train can only go in one direction.
Right.
There's no negative thrust.
There's no negative thrust. Certainly, that's an infeasible. So your policy cannot have a situation where your policy is negative. But I think the question is that what happens when you are solving an infeasible optimization problem? Let's say you are driving a vehicle, you reach a point where there is infeasibility. What are you going to do? Yes.
Maybe like you can prioritize the constraints.
You can definitely prioritize the constraints, but my question is, suppose all those constraints are still there, and so let me give you an example. I mean, maybe I'll give you the solution. So whenever there is infeasibility in your policy, you end up getting into an accident. Okay, so that's what happens. Whenever there is an accident, it means that you reached a point in state and action space where it was a point of no return. You have to end up getting into an accident. And it happens many a times. You know, you are doing distracted driving, not you specifically, but people do distracted driving. They are texting someone on the phone. Now their velocity is so much that they will cross the red light, they will jump the red light, and then there'll be an accident because some vehicle is going to crash to that particular vehicle that's jumping the red light. So generally speaking, one of the things that you always have to worry about whenever you are, and by the way, this is not another example, somewhat unfortunate example. So there was this autonomous vehicle, I don't know which one, but it was driving on San Francisco. A woman got hit by a vehicle she was a pedestrian. She was hit by a vehicle that was human driven vehicle. And then she fell in front of the autonomous vehicle. And the autonomous vehicle, of course, could not react within appropriate time. And then the woman was run over by the autonomous vehicle. So this is a real accident that happened in San Francisco. So that's another situation where through no fault of your own or through no fault of the autonomous system, it ended up being in a situation where the state xt changed suddenly with having a human in front of the vehicle, but it was a point of no return, and therefore the vehicle had to run over the person. So infeasibility is really challenging. Dealing with infeasibility is really challenging. As a human being, you can trust your own decision making instincts wherein you can deal with infeasibility, but when you are doing it on a vehicle, on an autonomous vehicle, on an autonomous system which is deciding this pi at every point of time, I don't think there is a generic rule of thumb as to how to detect and fix the infeasibility. So it will always be person to person and situation to situation dependent. But so throughout this class, we are going to assume that you're always in the feasible region and that there is always a policy that meets all the feasibility requirements, knowing very well that these assumptions could get violated, especially in situations where there is going to be an imminent accident. And that accident could lead to fire, it could lead to loss of chemicals, it could lead to blasting of some sort, like chemical factories. Sometimes you will have blasts in chemical factories and so on. In all those situations, you reach a point of no return and then there is infeasibility in the system. Therefore, no policy can actually save the system from the disaster. So anyways, that happens. Now, coming back to this particular expression, so you have a whole bunch of inequalities on your system. In your assignment 6, I have asked you to come up with, formulate an optimization problem with equality and inequality constraints, and then remove redundant constraints and so on. So you will see how a business problem gets translated into a dynamic optimization problem, and what sort of constraints comes into the picture. So something you will do in homework assignment 6. Now the question is, how do we solve problems of this type? So one thing that I'll do in order to solve this problem is I'm going to define a state dependent action set, and I'm going to denote it by ut of xt, which is the set of ut such that gt of xt ut less than equal to 0, ht of xt ut is equal to 0. So at every xt, I'm looking at all the feasible actions that are available to me, and
Do we solve this problem for a given X numbers? Like,
for a given xt. So currently I'm sitting at xt, this is my state. These are the set of actions that are available to me because they are all feasible.
I'm talking about like the problem of definition. Like we have like X, like initial condition X0, it is given.
Oh yeah, x0 is given. That's right. Yeah. Thank you. Yeah, x0 is given. So I want to start from OSU and I want to go home. So x0 is my position and velocity at OSU, which is 0, 0, or whatever. Whatever my GPS coordinates are, and the velocities are 0, 0. So that's my x0. Okay, so how do we solve this problem? Well, there is no change in the terminal value function. It still remains the same. The terminal cost is the terminal value function. The only difference now is Vt of xt is now minimum ut in uxt. utxt, yeah. C of xt ut plus Vt plus 1 of ft of xt ut. So this is the place where we make the change. So when all actions were feasible, it was an unconstrained optimization. So this minimum was over ut in Rm, but I'm no longer looking at ut in Rm. I've constrained the set of actions that are available to me, and I'm only minimizing the optimization problem over that restricted set of actions. And then the pi star t of xt would be the argmin of ut in utxt of the same objective function.
After we see key index to C. Yeah, right. So the mid.
Oh yeah, CT. That's right. Thank you. Yeah, index is right now. Thank you. So the current cost plus the future value. And how do I solve this problem with utxt? Well, the way to solve the problem is to write it in the usual format. I want to minimize CT xt ut plus Vt plus 1 ft xtut such that gt xtut less than equal to 0 and ht xtut equals to 0. So I'm given an xt right now. So this is my current state xt. So I'm going to replace this xt with my current state, and then I'll optimize over all possible ut. This optimization is over ut in RM. All of you know how to solve this problem? How do we solve this problem? You can use barrier method, you can use Lagrangian method, you can use augmented Lagrangian method. Whatever is your favorite method, sequential quadratic programming, you can use those to solve this problem. Generally speaking, if you are if you're going to a controls company, like a company that deals with control systems, most likely you are going to use sequential quadratic programming to solve problems of this type. So this is so sorry. So xt is the current state. So you substitute xt with the current state, current state, current state, current state, and then you solve for all possible. I mean, you solve for the optimal action that are satisfying these constraints using sequential quadratic programming. Okay. Any questions so far? Okay. So we have learned how to solve unconstrained dynamic programming. We've learned how to solve constrained dynamic programming. Because these constraints are almost always there in most of the problem statements that you would be dealing with in the future, I'm going to assume that whatever approximate dynamic programming technique you want to apply, you have to apply it on a problem where there are state action constraints. So let's look at the approximate DP techniques. If there are no further questions, I'll move on to the approximate DP stuff.
Can you talk more about the VT?
This VT, this is the value function. So remember in the dynamic programming, we used to compute the value function at every point of time, starting from the terminal time step. So at the terminal time step, this is how I define my value function, which is the same as the cost function. At any time t, I have to minimize the action of the current cost plus the future value. So this is value Vt plus 1 evaluated at a future state, right? So the only difference right now is earlier we were in the unconstrained case, so utxt was Rm, so we were solving an unconstrained optimization problem. Now I have these constraints, state action constraints, so now I have to solve the constrained optimization problem in order to compute Vt. That's the only difference. Okay. And then pi t star, which is the policy, optimal policy at state xt, it's the argument. So whatever is the minimum, you store it in the value function. Whatever is the argument, you store it in the policy. And so remember that policy pi t star is from Rn to Rm, because m is the dimension of the action, n is the dimension of the state. So it's a function that maps Rn to Rm. And if you have multiple minimum, you just pick whatever minimum is your favorite minimum, right? And that gives you the argument. Okay, wonderful. So I'll keep this formulation on the board, and let's try to talk about think about the lookahead approximation. So we have, so the problem is T is large, and so our solution is lookahead approximation. So let's go back to our favorite example, which is our rocket example. So I have to send a rocket from Earth to Moon. My capital T is 1 million. This capital T is 1 million. I can't solve this 1 million 1 million time step long dynamic programming problem because it's too complicated. And by the way, this problem was solved in the movie Hidden Figures. Okay, so keep Hidden Figures at the back of your mind. So they wanted to go to the moon, they had to send a rocket. They had a very primitive computer on a somewhat primitive rocket. It was pretty advanced from that particular time, but from today's standard, it was somewhat primitive. So we are going back to 1965, 67-ish era, and I'm faced with this problem. So what will you do? What are you planning to do to solve this problem? So we did discuss a few strategies in the previous class, but I want you to be a bit more specific and a bit more mathematical and tell me what exactly is it that we will do to solve this problem. Any thoughts?
You might
Yeah.
discretize the state space,
Okay.
but in a way that so X is not continuous,
Uh-huh.
and instead of R2,
Uh-huh.
we have like a bunch of little squares.
The problem is that if you want to discretize Rn, it's a very complicated process. You have an exponential blow up in the number of states you have to consider. Exponential in n, exponential in the dimension of the state. So even if every dimension you have 10 points, you have 10, the dimension of state is 10, now you have to look at 10 raised to 10 points. Very complicated.
They didn't do reinforcement learning back then.
No, there was no reinforcement learning back then. Yeah. Okay, so there are two train of thoughts here. One is called model predictive control. And the other one is rollout algorithm. Rollout is a bit general than model predictive control. Model predictive control is a class of rollout algorithm. But let's try to introduce these two classes of algorithms and try to see how to solve that problem. Okay, so MPC, what do we do in MPC? What's the core idea? So at every time t, I am going to solve the following problem. Pi t. Okay, so now we are doing approximate dynamic programming. So we are no longer doing pi t star because we can't compute pi t star. We've already given up on the hope of computing pi t star because I can't solve that 1 million time step problem. So let me use pi t tilde, okay? Because I'm not solving for the optimal, I'm solving for the suboptimal problem. So I'm going to do S equals to t plus tau Ct xt ut. This is the argument, sorry, this ut such that ut is in u txt. So just substitute these two inequalities, sorry, inequality constraint at the equality constraint here. There's something missing, right? So remember we were saying if I have to fly a rocket and I'm only looking at tau time steps, so tau could be 10, tau could be 15, tau could be 100, but a very limited number of time steps. What's the minimizing solution to minimize the fuel consumption of the rocket over the next 10 time steps? Just don't fire the rocket at all. That's the best solution. But we don't want to get to that solution. Our ultimate goal is to get to the moon. So how do I enforce the constraint that I need to be on path to the moon? What should I do?
You should have like a reference trajectory.
Yeah, we should have a trajectory. Perfect. So what I want to do is I want to have xt plus tau equals to x bar t plus tau. So this is the trajectory computed in advance. So even before I start thinking about the rocket, I'm going to figure out a trajectory that the rocket is going to take to get to the moon. And I'm going to enforce this goal constraint. So this is, think of it as a goal at time t plus tau. So my goal at time t plus tau is to be at this particular position in the space. And this position is, let's say, 100 kilometers above the surface of the Earth. Okay, so perfect. So at time t plus tau, I want to be at this particular point in the space. What's the problem with this approach?
You don't computing that with start.
No, I mean, you can change tau. Let's say tau is 10. So then computing this one is comparatively easier than computing 100 time steps. Initially, so t is 1 million. T is 1 million, but this tau is only 10, 1500. So comparatively much easier to solve. Yeah.
I think it's not good for strong perturbations if you can't reach the.
You know, the point is that at xt, I know exactly what my current state is. So and I'm only solving for the next 10 seconds or next 5 seconds or next 1 second of the situation. So not much perturbation can happen in the rocket space. You know, not much will happen in the 1 second or 10 seconds. Things will happen at a longer time scale. But there is still a problem. It has something to do with what you're talking about, but you're not pointing at the right direction. So what is the problem with this setting? Yeah.
What if that's not feasible?
Perfect. Amazing. What if this particular equality is not feasible? So because there was wind, crosswind, I am now at this particular state. I was expecting to be at this state at xt, x bar t, but I'm actually here. But now from here, I can't really get to x bar t in tau time step because of all the constraints that I have on my actions. I cannot fire my rocket more than the capacity. I cannot change the direction of the rocket more than what the ailerons are allowing me to do. So I cannot really change things significantly. So I can't really reach this particular state. Then what are you going to do?
You will build like a norm.
Awesome. Yeah, perfect. You can do a norm. What else can you do? Yes.
Could you just increase your horizon?
Wonderful. You can increase tau. Okay, you can increase tau. So maybe I cannot reach. So I'm standing here. Maybe in one step I cannot reach there, but in 2 steps I can reach there. Okay, because 2 steps my state has also changed. Instead of looking at xt plus tau, now I'm looking at xt plus tau plus 1, and hopefully I should be able to be feasible. I would be feasible for the updated longer horizon problem. So certainly you can increase the horizon length, or alternatively you can add a soft constraint. So maybe I'll erase rollout from here. So I'll add a soft constraint. Where I'm solving argmin ut in utxt, ct xtut. You know, one problem that I have is I'm writing it as ut in, I probably want to write us in usxs for all s in t plus tau.
Oh,
Because I have to make sure that this constraint is met at every point of time.
then the other.
Oh, this should be xcs. Sorry, please make the change. The time step is s actually here, not t. This one is correct, but this one is cs of xs us in capital US XS for all s in the time period from t to t plus tau. So here I am solving the same problem. S equals to t plus tau
we have that. So, terminal.
Yeah.
So lost.
Sorry?
Because we didn't define X. Oh, okay, we stated X bar is, so it's a number right there, right? X bar.
X bar is just a number. This is just a number. This is a trajectory that somebody gave me that at 10 seconds I have to be 100 kilometers above the surface and some specific GPS point in the space. So I have to try and get there at some point of time. And this Q is a positive definite matrix. Okay, you can pick a positive definite matrix and that makes things well defined. Now this is a hard constraint. This is known as a soft constraint. Okay, it's soft because even if you violate this constraint, even if this is non-zero, you're paying a penalty for it, but it's not going to make your problem infeasible. So here you run the risk that all US, you try to solve this problem and it turns out all US is not a number, not a number, not a number. That's not beneficial. Here you will not get that problem, but then this particular cost could be pretty high. Yes.
But this is very dependent on the queue, right? If it's
This is very dependent on the queue for sure.
it's too like not well designed.
That's
or
right.
very, like, dominant
Yeah.
over
Exactly. You are absolutely right. So ideally the Q matrix here has to be commensurate with the Lagrange multiplier for this particular constraint. Technically speaking, I'm being somewhat not precise here, but you can think of the eigenvalues of Q to have some relationship with the Lagrange multiplier here. And if your Lagrange multipliers are too high and you pick a Q that is too small, then this infeasibility, this value would be too large. And that's something you want to avoid. And when you are infeasible, typically when you are infeasible, the Lagrange multiplier turns out to be either infinity or minus infinity, right? So that's what happens when you have infeasibility in your optimization. So in fact, that's one way to check for infeasibility, which is when you are applying the algorithm and it turns out that your Lagrange multiplier is growing to infinity, then you know that you have an infeasible problem at hand and you have to do something about it. And remember, when you are in that kind of safety critical mission where hundreds of millions of dollars worth of equipment and maybe 5 or 10 astronauts' life is in danger, you want to make sure that all of this decision making happens within 50 milliseconds. Okay, so if you have infeasibility, how to deal with infeasibility. If you don't have infeasibility, you are able to compute this dynamic problem for tau time step and come up with a solution.
Did we include all the dynamics constraints and state action constraints? So like X.
Yeah, that's the state action constraints are here. What other constraint were you talking about?
Dynamical state.
That is always the case. So here, everywhere I'm writing this XS, you automatically assume that XS plus 1 equals to FS XS US. So this is implicit in all the expressions. Any other question? Okay, so this is known as model predictive control, very commonly used in a lot of different chemical control processes, or if you have to do process optimization in chemical plants, or if you have to do some vehicle optimization inside the vehicle, you use model predictive control to do something like this.
Anything linear?
Sorry?
Any system that is linear? This.
No, this one is even for nonlinear system, you can use this algorithm.
I mean, it can be used, but
yeah. Yeah, I mean, if you have a nonlinear system, you have a nonlinear system. I'll talk about linearization in some time. That's model approximation. We're not talking about it right now. And generally speaking, if you have a very complicated system, it's quite likely that you will use a combination of all these different approximation techniques that we are talking about. Okay, so you will do linearization, you will do model predictive control, you will use rollout algorithm, you will use some sort of approximation and so on. You will use function approximation. So all of this thing will be done in real world system, but we are treating all of these subjects separately for now. Okay. Let's talk about rollout algorithm now. So the idea in rollout algorithm is that you have a base policy. So I'm given a base policy. Pi bar 0, pi bar 1, pi bar capital T. This is my base policy. So I'm given a base policy. I'm going to compute the value function v tilde t of xt. I'm assuming that this base policy is feasible. So it's not an infeasible policy. It's definitely something that's feasible given the dynamics and given the problem statement that I have at hand. All the state action constraints are satisfied by this base policy. I'm going to define v tilde t of xt to be summation cs xs pi bar s xs s equals to t to capital T plus ct plus 1 xt plus 1. So this is the total cost to go with base policy. And I've computed this for all time t from 0 all the way to 1 million. I've computed the total cost to go for every state under the influence of this base policy moving forward. So if I want to go home, my base policy is going to be I'll go from here to Lane Street, then I'll take a left turn, then I'll go somewhere, I'll take a right turn, this and that. That's my base policy, and I'm going to assume that there is no traffic on the road and all lights are red light. Okay, that's my base policy. It's going to meet all the conditions of speed limit, this and that, whatever the constraints are there on this particular system. If I'm flying a rocket, I have some base policy that's given to me by some engineer, which says that here is how to fly the rocket and this is what you do. And you get to this particular point, then you take then you fire the thrusters here and you do this and that maneuver. And then after capital T time, you will reach the moon. And this is the total amount of fuel that you are going to burn under this particular policy. That's v tilde t. Now what I'm going to do is I'm at every point of time, I'm going to solve the following problem. I'm going to argmin of summation, the same objective function s equals to t plus tau cs xs us plus v tilde t plus tau plus 1 t plus tau plus 1 us is in remember, I'm minimizing with respect to the actions. So this argmin is being done with respect to all these sequence of actions that you need to take. But now you have your terminal cost is coming from the base policy. So we have three different algorithms now on the board. for look-ahead approximation. I have extremely long horizon problem. I have 1 million time steps to solve. I cannot solve that kind of problem on a rocket which is going to space. So I can use model predictive control where I have a set of time steps. I can pick tau. I can solve this summation of cost function as long as the terminal state is going to be the same as my tracking state that somebody has given me in advance. Then we face the problem that this seems to be infeasible. I mean, what if there is infeasibility here? So then I'm going to add a soft constraint here and then solve this particular problem, which is a soft constraint MPC. So instead of a hard constraint, I have a soft constraint problem. The third one is saying that, look, I don't have this trajectory computed in advance. Nobody has given me this trajectory in advance, although I can potentially use this base policy to compute the trajectory. Technically, I can do that. But let's say we don't have that trajectory. I have this policy that somebody has given me in the past. What I'm going to do is compute the value function evaluated at this particular policy at every point of time. So I have Vt of xt for all t. Now at every point of time t, when I have to make a decision, I'm going to sum the cost up to t plus tau. I'm going to add this terminal cost is going to come from this particular value function that gets substituted here at time t plus tau plus 1 with all the constraints, state action constraints that I'm supposed to satisfy at all points of time until the end of the horizon. So this is known as a rollout algorithm. This algorithm was being used to play chess back in 1990s. Okay, so it has a long history. Rollout algorithm has a long history, and it's a very powerful approximate dynamic programming technique. And the theory says that whatever policy I can come up with here using the rollout algorithm is going to beat the performance of the base policy. What does that mean in real world? I have a rocket, I want to send it to the moon, and the base policy, which was computed by somebody, said I need 4,500 tons of fuel in order to send the rocket to the moon. Okay, this algorithm will ensure that you need less than 4,500 ton of fuel. So 4,500 ton becomes the upper limit of what it's going to cost to get to the moon. So this one will always beat that performance of the base policy. Okay, that's the benefit of a rollout algorithm. So what we have done so far, I think the time is over. Yeah, so the time is over, but I think everything is clear. But are there any questions before we depart? Okay, perfect. So we did the look ahead approximation today. On Friday, we'll talk about model approximation, and we'll see how model approximation can help us solve this problem. Thank you.